Well, good morning. Uh, we are Team LAMBOT 3478 from San Luis Potosí, Mexico. And today we are going to talk about the most important aspects of the autonomous, as well as how we have developed ours throughout the years. So for those of you that haven't had the opportunity to come in contact with it yet, the autonomous is the stage of the match where the robot is controlled purely by a pre-charged code rather than having the drivers control it remotely. This is generally the first 15 seconds of the match, and normally the points scored throughout this stage are worth more than regular points. So that is why it is very important to make a good autonomous.
So the infinite recharge challenge of the last season is in what we are basing for this talk. So what was the challenge like? In the challenge of infinite recharge, you had this map and you have a lot of power cells in the field. So you had to pick them up and shoot into the power port, which is the image displayed in the right. So in the autonomous period, actually, you have to do the same thing as in the actual teleoperated period, but instead with pre-charge code. So the teams had to develop a code to collect the power cells in the field that were positioned in some default places and then move towards the power port to shoot them, and you will score double points for this. So this was like a big opportunity to make some extra points.
But what if something goes wrong? Something we want to make very clear is that making an autonomous is something that takes a lot of effort and time. You cannot expect to have a good autonomous if you only dedicate a day or two into coding of your autonomous. And also, making a autonomous in a hurry and not dedicating enough time can lead to some very bad outcomes that can negatively affect not only your team and an alliance, but also the spectators, because it can put their health at risk, as we're going to see in some of these examples.
All right, we're starting autonomous mode in match number 6.
Here you can see that the robot not only broke the field, but it also went outside, and it's a safety issue because an FRC robot weighs a lot and it has a lot of moving mechanisms. So if your robot goes out of the field and goes near the crowd, it can be a lot of risk and someone can get hurt very badly. Okay, so now here we have another example. This one is not as dangerous or has as many consequences, but it's still something that can go very wrong if your autonomous isn't well good.
Power up.
Qualification match number 36. Starting off with the Blue Alliance all the way across on the red side of the field.
For those of you that don't know, in this challenge, what the robots had to do was they had to tip the scale towards their color. And here, as you can see, the blue robot during the autonomous tipped the scales towards the red alliance color, which is obviously very bad because you start giving them points and not to your team, which gives them an advantage. And it's something that also can go wrong. And that is why you should take time into programming your autonomous correctly. And here is a final example. This is an FTC competition, so they are smaller robots, but it's also a good example of why you should take a lot of time to code your autonomous correctly. Here you can see the robot fell down, and many robots in FRC and FTC cannot get themselves back up. So if your robot falls down during the autonomous, your robot is basically useless for the rest of the match, which is very bad because now it's at 2v3 instead of 3v3, which gives the other alliance a huge advantage. So what are examples of good autonomous? Here we have two examples from teams 254 and Team Maverick of good autonomous. Something I want to point out is that good autonomous doesn't have to do everything. A good autonomous should be focused more on consistency and doing few things, but doing those few things the right way, as you're going to see in this example.
So light 'em up, light 'em up, light 'em up. I'm on fire. So light 'em up, light 'em up, light 'em up. I'm on fire.
Here you could see that the robots didn't do the craziest of movements, but what they did do was they put themselves in position to be able to shoot the 3 balls very consistently, which is something that guarantees you points at the beginning of the match, which is better than trying to do all of the activities possible, but ending up doing all of them wrong and not gaining any points at all. So it's better to be consistent than to be greedy and try to do everything. However, on this next example from Team Maverick, you're going to see that they actually do a lot of things, but they actually do all of those things the right way, which is like the best autonomous you could aim to code. So here it goes.
Good. Send it. 3, 2, 1.
Yeah, it's very impressive what they were able to do, but I want to point out that you should never try to do more than you can do consistently, because it could be it could hurt you more than it benefits you.
Types of autonomous. So depending on how they work internally, we can classify the autonomous in various different types. Firstly, we have the time-based autonomous. These ones take into account how many seconds you want your motors to be rotating. And with that, you can move a certain amount of distance or turn in a direction. However, they tend to be imprecise because the amount of rotations a motor can do in a certain time also depends on external factors such as the battery, the state of the motors at that moment, and other things. That is why some teams prefer to use encoder-based autonomous. Encoders are some sensors that measure the amount of rotations a motor does, and similar that with time, you program it to do a specific amount of rotations to move a specific amount of distance or turn in a direction. Then we have motion profiling. This one is a little more specific because it takes into account variables of your own robot, the acceleration it can take, the maximum speed it can go, and uses those parameters to calculate a route for the autonomous. Then we have some special cases. Computer vision, which uses a camera to identify certain targets in the arena. For example, in the 2020 Challenge Infinite Recharge, the reflecting tape that was around the power port would allow you to identify that as a target using computer vision. Then we have the Sandstorm Challenge in 2019. In this challenge, there were some blinds that were drawn at the autonomous period, and so the drivers could not see anything. However, you could choose to either create a normal autonomous or install cameras on the robot and allow the drivers to drive through the feedback of these cameras. And finally, some teams decide not to do an autonomous code at all. However, this isn't very advisable, since even though you have to take a lot of time and safety principally into consideration, many times you can earn points by simple tasks such as crossing the starting line or other simple tasks that wouldn't require much coding and can give you an advantage at the beginning. So going without autonomous isn't really a good option.
Well, now we are going to talk about the components of an autonomous. And one of the most important parts when you are designing an autonomous is creating a path. In general, it is about defining a route with the points through which the robot has to pass. Having a path to follow is the basis for building a good autonomous, because we can make a visualization of what the path that we want the robot to move through. In a path, the places that the robot has to reach are decided, and you create different waypoints through you have to move in order to reach the objectives. For example, in the 2020 challenge, taking the starting line as a first point, we can design a path to collect power cells, to aim, and other different tasks that we can complete during that 15 seconds. Another thing that we need also to consider is that now, once that we have the path defined, it's also necessary to clarify the way in which the path will be advanced. The trajectory is the specification of the quantities and the parameters of the robot. In general, this component is based on vectors that have defined the magnitude and the direction of the movement, which is why they are the key to define the parameters and how we are going to move through the path. For example, if a path has a curve, like in the image, the velocity has to be less than in a linear trajectory because you have to turn the robot and then continue moving. Another example is the time. If you are going to collect power cells in a certain position of the field, then you have to spend more time there because you have to activate the mechanisms that get the power cells and continue the trajectory. So this is why keeping this in mind helps you a lot when you are trying to decide how the robot is going to move to the path, and the trajectory helps you to see time, velocity, acceleration, and many other aspects that you can like define here before you start coding.
Okay, but as we all know, we don't live in a perfect world, and all of our robots have inconsistencies that can affect the path and the trajectory we want it to follow. That is why we need to use some utilities to help it stay on track despite these inconsistencies and mistakes that it can make. For this, we use something called the PID, which stands for Proportional Integral Derivative. Proportional means that it's going to correct the mistakes proportionally to how far it is off the track. Integral means that it's going to store every mistake it detects that the robot is making. So if at a certain point it detects that it's a few centimeters off from the expected path, it's going to remember that the code, and the next second is going to do the same, and so consistently. And it's going to add up all of these mistakes. And with this addition, it's going to correct the path of the robot so that it actually does what we want it to do. And finally, the derivative is also another way of correcting the mistake, but this one, instead of basing on all of the previous mistakes, it is only based on the last mistake that the robot did. So using the integral and the derivative, it's going to correct, and it's going to be proportional to how far it is off from the path or trajectory. And another thing we use is the motion profile, which helps us find out the different variables from a robot, such as the jerk, acceleration, velocity, and position. We need to know all of these variables, because if we do not know how fast a robot can accelerate, or the different velocities or the positions, we're not going to be able to keep track of where it is and if it's actually following the path or not. And also, without knowing the velocities, we do not know how much time it's going to take, or how to get from one point to another as quickly as possible. So that's why we have the motion profile and the PID.
The evolution of the autonomous in FRC. The way that the autonomous is coded has changed quite a bit throughout the years. The first important point we can highlight in this history is the spring of 2015, that is right after the season, when Team 254, the Cheesy Puffs, of which you already saw a video earlier, did a presentation on their autonomous, which on that year was based on motion profiling. Then the next year, WPI Lib, which is the library that the competition gives us to code, released Pathfinder, which was a tool to create autonomous. However, it still had quite a few errors, and many teams did not use it. They prefer to continue using time and encoder-based autonomous. Then some time passed, and on 2018, there was something remarkable. Team 254, of which we have been talking, accomplished a season without ever losing a match. And that summer, they released their code for the autonomous that they used. So some teams started to implement it right away, and others decided to continue with their usual way. However, just 1 year later, WPI Leaf made a whole library based precisely on this code. And that is how we get to today, where we have a trajectory library that works quite well and is far easier to use relative to what we had previously.
So now we are going to describe you in general terms how to create an autonomous routine and how to develop your autonomous throughout the season. So the first step is to creating a trajectory, and you can relate this to the previous definitions of path and trajectory given by my teammates. So initially you have the first image, some points that we call waypoints defining the path. These points are separated like a lot of distance, but you can use them to define the path in general terms. So you pick some points that are part of the trajectory, and through an algorithm that you can find in WPI library or in some other papers, there you can use these algorithms to inject more waypoints. So this is the image from the center, where you have some few initial points, but through the algorithm following the trajectory, you can insert more points to make the trajectory more precise. And then, because these are based in a robot that is that has a drivetrain of tank or West Coast. So these robots that we are using to describe these trajectories are robots that can only move like forwards and backwards and turn. So a robot of this type can actually go like move to the right or move in some angle, but they have to turn. So basing on the last image, you have like this smooth trajectory, and this trajectory represents a more real approximation of what it will look like in a robot, in a drivetrain that can move in only one axis. So in the last image, where the waypoints are being smoothed, these are for the movement of the robot to be more real, to be more realistic. So after these things made by the algorithm, the robot can move in that direction. Into the next slide. So after creating the trajectory, and well, in the trajectory, you have like these points smoothed, and each of the points have an ideal state. So each point you predefine in what position is and what time will the robot get to that point and at which velocity. So all of the trajectory is already planned, but as we mentioned earlier, the robots are not perfect, and they have a lot of errors that we can use to actually improve our trajectory. So if at certain point the robot has to be in 5 seconds and at some speed, you can base this error to move towards the next point and try to correct this error. And in these images, you can see one of the algorithms, one of the techniques used to follow the trajectory. So in the first image, you have the waypoints in gray color, and the actual part of the robot is in blue. The look ahead point, which is the orange point, is a waypoint that is part of the trajectory that is some steps ahead of the robot actual position. So if the robot is currently in that position and you have like a point that is further away and you have to follow that point. So it is not like you follow the path in the normal way that is, but you follow some other point forward. So the robot has time to correct it actually, and to reach the trajectory. These are like a comparison of the different types of look ahead. So the first one is in the second image that is down below. You have like a small look ahead that is following a point that is closer to the robot, and you can see the trajectory that moves not that smooth. And in the second image below that, you have a large look ahead, and the actual path is not that, it's not exactly as it was described, but it's better than the first image. And in the last image, the one in the right, you have the description of these definitions, the look ahead, and how you can search it. So if the robot is in one position, you can draw like an imaginary circle in the, and it has to intersect the actual path. So in that point where the path and the circle intersects, the robot must follow that point, and this is done obviously through an algorithm that searches a point and follows them. And later we will describe you how our team use these definitions of look ahead, of trajectory, to implement our own autonomous.
Finding velocities. Now that we have the trajectory that we are going to follow and that we know how to follow it through the look ahead point, we must define at which speed the robot will travel the trajectory. For this, we have to take into consideration both what we need our robot to be doing. So for example, if there's a turn, we might want to slow down. If there's an obstacle, we might want to avoid. And also what a robot is capable of, the acceleration and the speed it can achieve. So on the upper image, you can see that the max speed that the robot goes through is the blue line almost at the top. However, the robot can't move at that speed the whole time because it was in a resting state before. So it has to accelerate to reach that speed. That is the increasing red line at the left. Then when we want it to stop, we can't suddenly shut it down. We have to make it slow down gradually, and that is the green line. In other cases, we might have an obstacle or something we might want to go through. So in the lower image, we can see a purple rectangle, which represents something that the robot must go below. We have the yellow line, the yellow upper line, which represents the speed we want it to go. So for example, it is accelerating, then it goes really slow through the obstacle, and then it picks up again. But then as the robot can't just change speed like that, the blue line defines the speed that we are actually going to go through, through less velocity, but that it allows us to go down and then continue from there. So that is what we have to take into account, what we want it to do, but the capabilities of a robot have to trim it down.
Well, now after taking all these steps, a very useful tool when you are designing an autonomous is the odometry, because this technique uses encoders to calculate the distance traveled by the both left and right sides of the road in order to know the total distance that the robot has traveled itself. And with this information, you can calculate the position of the robot in a plane using the two simple formulas that we have here. That is the distance multiplied by the cosine of the angle of the robot. And for y, you have the distance multiplied by the sine of the angle of the robot. And maybe you are wondering how to calculate this. And despite you can use math and trigonometry to know the rotation angle, there is a better option using the Navex sensor, which gives the angle of the robot after a certain time of the field or movements during the autonomous period. The advantage of using the position of the robot to create an autonomous routine is that with a previous path and using a looking ahead method, the robot is able to define how far is from the original route and make a more precise correction. In a situation like in the one from the first videos, where the robot goes like literally out of the field, odometry can help you to determine where is exactly the robot moving and make an approximation. For example, in that case, you can shut down the autonomous if the position is out of the limits. And this gives you a lot of advantage. For example, during a match, if you find an obstacle, another robot, or you get out of the planet route, you can shut down or make a graded correction in order to change the way your robot is moving, or even stop completely so you don't generate, like, for example, problems like in the first video. So this is a very useful tool that you can use to find where is the robot moving in like almost all time in the field. And obviously, the last step to finish the autonomous period is make corrections in the trajectory. We have mentioned before that the robots are not following always the path that we designed. There could be power cells on the route, another robot, maybe the battery has low charge, and many things that you need to check in that part. So the final step is to use, in general, the PID controller that will give us the right like corrections that we need to do after we have applied all the other steps. So here in the video, you can see how does this robot is working. So here, for example, the original trajectory was to do like an S around that green rectangle. And in certain moment when the robot is moving, there is a point where it's going like out of the trajectory. And in that specific moment, the robot turns all the chases in order to move to the other direction that the robot was supposed to follow. So that's why it is important to use maybe the PID controller. In this case, is a barrier option, because you can make corrections based on the errors, as we mentioned before. And this gives a lot of advantage, because you can make the right corrections in order to follow that trajectory that we are looking for.
So now we will move into our specific autonomous development. We will later share with you some of the links we base this last review for autonomous, but now we will focus in our autonomous code for the season of 2020 and how the team LAMBOT 3478 developed to achieve what we did in the season. So first, the team of LAMBOT has some history of autonomous. We hadn't always developed like a good autonomous, but in the last years, the team worked hard to achieve some things. For example, in the year of 2018, there you have a video of what the team developed during that season.
The tiebreaker here on Turing for quarterfinal match 2. 2046.
Well, the team LAMBOT is the one that is on the left side of the. It's one of the blue teams, and is the one that is above and put a power cube in the scale. So in that year, we developed a routine that moves to that point and puts and places the power cube inside the scale. And in the year of 2019, we first work in the sandstorms with the drivers, but later we developed an actual autonomous routine for it to be more precise.
We're up for 101st match of the day. Counting this one, we've got just 10 left to wrap up the Turing subdivision over here.
And the team LAMBOT is the one on the left side and below that is placing the
Daedalus and Sir. Nope.
Okay, so in that year, our team first work with the sandstorms in the field regionals, but in the qualifications in the championship of Houston, the team got to develop an actual autonomous routine, and it worked a lot better than with sandstorm, because the sandstorms depends on a lot of other conditions, but with a working autonomous you can achieve some more. And then moving into the 2020.
Okay, so now let's talk about 2020. In 2020, as I mentioned, we need a lot of time in order to develop our autonomous code. But as many of you know, the robot of the competition isn't ready until the last few weeks, and there's not enough time to create an autonomous. So we had to improvise and create a small drivetrain using spare parts that we had inside of our workshop. And that is what I'm going to show you right now in the video. So what was really important for this drivetrain was that it was a West Coast drive, and that it could also pass those tubes, because those were in the middle of the field, and that was something very important in order to have a good drivetrain that could actually do the same things as the final robot would be able to do. So in 2020, we decided to test out the Pathweaver utility that is in the WPI libraries. Spoiler alert, we couldn't get it to work. We just weren't able to create a good autonomous using Pathweaver. So the next step was to start researching and see what we could find from other teams and other documents that could show us a better way to do an autonomous. And during that research, we came across this paper from Team Dogma 1712, in which they explained their autonomous process and what they did. And based on this document, we were able to adapt it to our own needs and create our own autonomous that we use during the season. Something else that we did for the first time in 2020 was we started using a simulator in Unity. This allowed us to test out different paths and trajectories without having to have the physical robot ready. Despite having the drivetrain, we also used the simulator because we could test things quicker without needing to actually be on the field, which was sometimes busy, or it was just not the most convenient thing to do. So now I'm going to show you an example of a trajectory in the simulator. There you can see the different points of the path that the robot is following. And that's what we have been explaining during the whole presentation, the paths and the trajectories. And here's another example. The green dots are the original path, and the blue dots are the smoothed path that is the result of the algorithm. There you can see that the robot has a more natural movement because it's following the blue dots and not the green dots. And here we have two examples of trajectories that did not work. These are mostly due to mistakes like the robot not being able to find the next look-ahead point and getting lost, and as a consequence, it shuts down and stops following the trajectory, which is good for safety protocols because otherwise it could start doing weird stuff and someone could get hurt. Here is another path that also the robot just loses the path and stops.
And well, after a week of work, almost, the team was able to correct most of the mistakes in the simulator. The result is the one that you are seeing at the right image. The team designed different autonomous routines depending on the strategy during the match. And the video will show a routine that was previously shown before, but with the suitable corrections in order to complete the trajectory plan.
A ver, déjalo. ¿Listos? Ahí va. Una, dos.
Okay, well, if you pay attention to the way the power cells moved, you may have noticed that mostly the last time the robot shoots the balls, yeah, it make like a strange curve, not too much realistic, in order to enter to the power port. And these details are the ones that reduce the precision of the simulator compared with the real match because of these kind of variables that we are not considering. But despite this fact, the simulator is a very useful tool because it allows the team to make approximations of the trajectories and its utility during a match. We can compare times, points earned, movements, and other details that could be corrected even before the road is ready. And with this, we have the best autonomous possible, obviously trying to make corrections and then applying directly to the robot instead of make different tryouts and then have the autonomous. And during the last year, in Infinite Recharge at Home Challenge, in the next slide, we can see a video that we created explaining how does the simulation in Unity works and compare it with the real match. So in the first video, you will see Lambot on the Blue Alliance, bottom right, making the routine that we plan.
I'm trapped in my box up against the wall. I see no solution or exit.
Here, Lambot is on Red Alliance up to left.
The pressure's growing exponentially. I'm trying to keep up to speed with you. Your lane changing is accelerating me. I'm hitting the ground and I'm sprinting. I'm falling behind.
This is the route that we plan for the road. So as you can see, during the first routine, the road has to shut down the autonomous before it finished because certain details during the match. And during the second routine, you see that it was like a movement with the power cell. So the autonomous for safety also shut down before it finished the routine. But the work in the simulator, it was very similar to what we really applied during the season. So this is like a way you have to visualize what is going to happen during a match before you go to the competition, and it gives you a lot of options to work with.
And finally, during this year's Infinite Recharge at Home, it was this video, along with the presentation with the judges, what allowed us to earn the Autonomous Award for the simulator and the multiple paths that were created in the event that one did not work, or we could choose another one during the match, well, right before the match.
Nice.
Okay, so now we will show you how the simulation in Unity work, and you can have a much a better idea of how it was working. Let me share here my screen. Okay. So here is the Unity simulator. Unity is a motor for video games, and you can develop, well, it is more commonly used for making video games, some which are very famous, and you can do like 2D video games or 3D. So after reading these papers, we search, and after a lot of work for several weeks, we came out with this solution, that implemented all of the previous steps that we work and all of the math required to make a good autonomous. So here is the UI for Unity. You can have like different objects. This is the field, and we didn't do that. We imported from the files that FRC releases. So you can like modify all of the parts of this, and you can actually have different types of objects. This robot, for example, is not a robot, but it is a model of a different robot that we were using. And you can see like a preview of all the field. And here are the power ports for the power cells and the scale, the rendezvous point. So now we will show you the different scripts. This is a project in Visual Studio. These colors are like customized, but it's the actual interface of Visual Studio that you normally use for developing code in FRC. So here we have the project for the Unity. And you can see like this is a really large code, but it implements all of the different math and all the calculations required to make a path. So here in these folders, we have all of the autonomous that we developed, and each one with a different name and the number of power cells that it can score. And here we have the paths, the different points that were used to make a trajectory. So for each trajectory, we have like different paths with different points, and all of that were working to score a certain amount of power cells. So we will show you an example. Okay, so here, if we center this for it to look better, this one of the autonomous routines we use, and it displays the points required, shoots the balls when it is full, and then moves to get some other power cells. And this was the final path that it did, the robot. And so here in red, you can see the actual waypoints, the points required for the trajectory that we showed you. Then the green points are the injected points to make the trajectory more precise, and the blue points are smoothed, so it follows an actual robot trajectory. And over here, you can see all of the different paths that the team worked. In this selector, we have like something to do nothing, something to create an S path. That was one of our first tests. Here the robot moves to make that group. And for example, you can see another paths that were in different positions. For example, here we started in the right side of the field, but we have some other trajectories to start in the center of the field. So here it's showed these balls and collected these other power cells over the center of the switch. And sometimes the robot does that are some errors, and we corrected them to work. In this example, the robot starts in the center of the field and collects some balls, some power cells that are over here. Of all these 21, I think, trajectories, we only implemented like 3 or 4 in the actual robot because it requires some other variables, but we try to make the autonomous as approximated to the reality as possible. So in this file, for example, we took into consideration some other parameters that are useful for it. For example, the maximum velocity, the maximum acceleration, and that um, are variables that affect the robot final movement. So in the WPI library, for example, here we have a presentation that we based for some of the investigation we did. So over here, we have like the maths in the actual maths that we use for it to develop. And for example, we also use the drive characterization for WPI library. So let me get this. Okay, so the robot characterization is another implementation we made for in the WPI library that it is actually an interface. It is really easy to use. You only have to download some project to your robot, configure for your motors and your specifications. But after running this little program on your robot, you can see that the outcome is a log of data that shows you all of these variables, like the maximum voltage your robot can reach, and it traduces in a maximum velocity and a maximum acceleration. So after knowing these variables, you can set them in the simulator and in the actual code and recalculate the routes for it to be more precise. So for example, in these routes, well, these are actual points. Here you can see like the XY coordinates in the field. And after implementing all of these and putting it together, you can run the autonomous. Here in this script, you choose like only one routine, and in this implementation, it uses like all of the algorithms. Here you can see the look ahead, the curvature to calculate the actual velocities, and it is a whole process since the beginning of you set the different points for your path. Then the algorithm smooths the path according to your robot, and then it follows according to the robot actual specifications. For example, we have another implementation that are not active currently in the simulator. For example, is the PID, and there we have the constants for it to be more precise. And we have this variable that is noise. Well, the noise is something very common in FRC, and more with another teams working together in the alliance. So you can have like a lot of variables involving your final code. So for example, we can test, well, let's try this route, for example, and active the noise. So the actual path will be a little more real world, but there you can see the noise that the robot is actually struggling to move. This is like really exaggerated noise because usually you don't have like moving like all the time, but we use these approximations to be more sure about our simulation. So now you can activate or unactivate, and with all of the implementation, the PID and the look ahead, the noise is actually not that, it's not something so our autonomous wouldn't work. And you saw it in the other video, how it actually worked in sometimes in the actual competition. So with this implementation, we plan to use it in the following years for it to have an idea of our autonomous previous to the actual robot to be ready. And well, there are a lot of other simulators, not only Unity, you can implement to try these solutions. And it is actually some other in the WPI library. So we will share with you the references that were in the last page of our presentation. So you can have you can search all these implementations and do create something for your autonomous period. So if you have any questions, we are open.
Thank you very much, Adan. Also, Christopher, Jesus, and all of your team 3478 for being here today with us. They are LAMBOT from San Luis Potosí in Mexico, and this was the autonomous presentation they prepared for all of us. So again, thank you very much, guys, for your time and for being here in the FRC Warm-Up 2022. Remember, you have the opportunity to send your questions to the presentators via the Q&A button in the webinar. And we have already received the first question from Andrea Elizalde that asks us, do you focus on programming your auto before the teleop?
Well, I can answer it. We actually have, the whole team of programming in our team, it's divided, but we work previously on a drivetrain with and implement like code for the teleoperated because it is actually based on the same code. Like we have some differential code for the drivetrain that we work in teleoperated, but as we have been developed this code for the teleoperated for several years, it is not that it takes us a lot of time. So we create like a simple code for the drivetrain, and then we move, before the robot is ready, we move into working in the autonomous with these simulations because we have like no access to the robot before, in this time of some weeks.
Awesome. Thank you very much. We are still waiting for more questions from the audience. So in the meantime, guys, are you ready for this new season, 2022? What are your expectations?
Well, we consider that it's very exciting because after a year where we don't have like a live competition, is the emotion of what is going to happen the next year. So yes, we're waiting for the release of the challenge. We're preparing some stuff on the workshop, and we're trying to do our best because we think that the next season we have many opportunities to work in different things that, for example, we have been working during the last years. So yes, we are very excited.
We're all waiting for the best. So if you allow me, I have another question that says, if we are a rookie team, what would you recommend us to focus on regarding autonomous?
Well, for example, the basis of an autonomous, you have your project of the robot. So the autonomous works in the certain orders that you are giving to your robot. So the first step that you have to think on is to create a simple path and a trajectory, because it's the idea that you have to follow or you want your robot to do. Obviously, if for example, you have in this last challenge, you have the starting line and your robot is behind the starting line. So one of the most simple steps that you can take is create an autonomous that, as we said at the beginning, can cross the line in order to earn those 5 points that anyone will give you to your alliance. So that gives you the opportunity to earn that point. And then you can start trying with different paths and simple paths to know how you're going to reach, for example, in this challenge, power cells, and how does your robot has to move. For example, you can base first on a time and encoder autonomous to try out the trajectories, and then go start like drawing the difficulty of the autonomous and try, for example, motion profiling, the PID, and create all these steps that we have mentioned it, but from a basis where you can like control the variables and know how the capacity of your robot is to move, like for example, through the field.
Yes, I would like to add that, well, as we mentioned earlier, it is important to have something like securing autonomous rather to aim for a score like the maximum points available. So yes, the recommendation will be that to first work in simple movements such as going forward, going backwards, turning, and well, getting it into an algorithm. So you can now set, for example, move to some meters, move like 5 meters, and according to your robot specifications, to your wheels, you can move exactly to that position and also to turn to some degree. So by having the basis, like you can move accordingly some distance and spin some angle, then you can integrate that steps towards a more complete autonomous, like first a simple routine and then going upwards to scale it and to create a more complete autonomous. But usually in these challenges of FRC, you earn 5 points for only crossing a line or for moving or doing something. So that is like the first step to achieve those points, and later you can work towards a more complete autonomous routine.
Awesome. Thank you very much. And our last question, also from a rookie team, says, do you consider any programming language better than another one when coding the autonomous? We use LabVIEW.
Okay, so we have like 3 main languages in FRC. I'm pretty sure you know them. It is Java, C++, and LabVIEW. So for LabVIEW, personally, I wouldn't recommend it that much because it is a graphics code. I think I am aware that it is a graphic type of coding where you have like different blocks with different actions, but it is not that complete, for example, that you have in C++ or in Java. In LAMBOT, we use Java because we have been using for a lot of years. We have plenty of our implementation, our algorithms in Java, and it is actually really it is a really organized syntax that we manage in Java because we had like all of these different objects, scripts, and this structure has been useful to us. But between Java and C++, I will recommend some of those. But if your team could be learn another one of these 2 languages during the season and during this break period, I will recommend you to try some of these languages. In the WPI library page, you can find all of the documentation needed. It is not that difficult to implement like command-based robot and another algorithms. I encourage you to explore this page, the WPI library main page. I can share them with you. So well, here's the link to WPI library, and there you can like learn all of the basic stuff for Java and the programming in general. And there are some sections that are called trajectory and that are more advanced, but I encourage you to visit some of these links that we share with you.